Okay, so we have this capacity source switch. Assume capacitor is initially uncharged, at least carries a charge. It gives it a voltage that's not equal and opposite to the voltage of the source. So what's going to happen? Well, what actually happens if this metallic capacitor, where electrons are going to be the moving charges, is negative charges are going to be attracted toward the positive side of the source. Okay, so you got full negative charges. Well, negative charge is going to be attracted here. It's going to create an electric field from here to here, and you're going to have a migration of charge. You're going to lose negative charge here. This will end up positively charged. When the negative charges get here, the chemical, the battery, or whatever your source of EMF is, then pushes them to the negative. Okay. And then they're repelled by the negative plate. Okay. And end up with. So what you end up with, after some time, is that positive charge here, and that negative charge here. Okay. There's going to be a voltage across there. Here's a voltage across here. Now, if you go around the loop, what happens to your voltage? If we go counterclockwise across the loop, go from positive to negative voltage, so you have a voltage drop here, right? And then you go around here and your voltage rises. Okay. And that process, well, you're going to be pumping charge until the voltages are equal and opposite. So you have an equilibrium situation when voltage rise here is equal to the voltage drop here. Okay, because at that point you have no electric field anywhere in the wire. Makes sense? Okay, so which is from negative charge full for the positive terminal of the battery. Okay. Charge held. Now this is positive, this is negative. The electric field, the wires is zero. So we have voltage drop. VS cross here. And if you going around here like this. Have the voltage rise. BS, when this is an equilibrium, okay? Does that make sense? Clarify a little bit what's going on? Okay. How long does that take? Of course, you would think, according to the differential equation, and everything else, that you would exponentially approach full charge. You would exponentially approach it, but you'll never actually theoretically reach it, okay? But in practice, pretty much you get the last electron there after enough half-lives, okay? I take a whole lot of half-lives to get it there, but you get out to where there's a negative difference after, say, 10 half-lives. There's no resistance in this circuit. Okay. Now that's kind of an ideal situation. If you had superconducting materials throughout here, well, you wouldn't want to use a battery because near absolute zero, the chemical reactions in the battery would lock up long before you reached necessary temperatures. Okay. Although, I mean, if you're in the liquid nitrogen range, you might get something more. But you could maybe power by induction. You have some coils there, have a magnetic field oscillator to get induction. And somehow generate a voltage with the result of current charges. Okay. And if you feel good and that's all stuff, you might be able to maintain something like a constant voltage, although you probably have to use rectifiers to get a direct current. That's going to be messy. So practically, you probably really can't do it, but let's just ignore that. So suppose you could. Okay. So then with this charge instrument, if there really was no resistance and we could maintain a constant voltage. Okay, so we're thinking through an ideal case where you have a constant source voltage, zero resistance throughout. Okay, well, example, put everything in liquid nitrogen, liquid, whatever, and make everything superconducting. You're not going to use the battery, but maybe you can do some conductive source of potential difference. Conductive source at the end from an external magnetic field. But still not really achievable because you kind of have to reconcile it, get a constant, yes. Not reconcile it, rectify it, and no rectifier is going to give you constant smooth voltage and to work out that temperature. I don't know. It's been a long time since I've been in superconductivity, so I've kind of forgotten how it works. But let's just assume that it was achievable. Would it be possible then to have instantaneous charging? Okay, so had some pretty good responses here. Okay. Uh, talking about the current, yeah, and it's current, all that times zero. So we're right on the verge of saying what needs to be said, okay? It's just, okay, well, my question then was, can you have infinite current? And maybe I followed up with, well, how fast would the electrons have to be moving? Well, you got a finite number of electrons, or a finite number of electrons in the universe, okay? Certainly a finite number of electrons within the circuit. So to have an infinite current, so that this thing charge instantly, you would need to have electrons moving infinitely fast, okay? Uh, electrons move infinitely fast, and you got a really good quick response there, so no, limited at least by the speed of light. So right there is a limit. Okay. So questions? Instantaneous charging possible. Require infinite current. Charge carriers is finite. Number of particles in the whole known universe is only like 10 to the 86th. If you ever take a few powers of 10, it's around that. Okay. So you know you don't have even 10 to the 100th charge carriers available. So you certainly don't have infinitely many charge carriers available. The number of charge carriers is finite. So in order to charge, so charge carriers need to migrate at infinite speed. And limited by speed of light, so no. Can't have instantaneous charges. Is there anything else that limits how fast you can charge the capacitor? Okay, so they're the limiting factor. You got finite power. And you were right, you know, the ideas you were expressing were closely related to this, okay? But we need to sort out the concepts, you know, the energy to charge it is not in the current versus intermediary. The energy we need to charge it is here because assuming we do need energy to charge it, okay, it's going to come from your source. Now, if you got some external magnetic field driving some induction type thing in here, in your superconductor, probably complicates the task, keeping the thing cold enough, but I think you get by that. It doesn't have to be that cold, liquid hydrogen is that cold. That's zero. Mascots understood. Pollen, causing the cough. Trying to avoid that. Class. In any case, does it take energy to charge a capacitor? Well, we talked about it. And let's just review. Uh, oh, we did the chapter on capacitors, 16, I have. So you want to kind of keep that in mind. And the other concept is that electric fields have energy. Capacitor has energy. Didn't have any energy when it was on charge. Charge it up. Take it out of your liquid nitrogen bath or whatever you use. Okay. Maintain the charge somehow. Not sure how feasible that is, but you know, maintain the charge and try to zap something with it. You'd be able to. Okay. Try to get a current. You can measure. Okay. There'd be one. And that current would run through a resistor. So you'd be using up power that's stored in the capacitor. You also, I think, would at least peripherally seen the idea that the electric field in the capacitor then has a certain energy per unit of volume. Take the volume between the plates, divide by the energy. There's the energy of your electric field. Okay, electric fields have energy, whether between plates of capacitors or not. It has an energy while it's between the plates of the capacitor. If you produce the same electric field, it's going to have the same energy per unit volume as if it was between the plates of the capacitor. Take just a region surrounding an isolated charge. At the right distance, you've got an electric field in a tiny increment of area or volume. Okay. It's going to have an energy per unit volume. Okay, well, anyhow. So you kind of want to carry that because I think some of you are looking at electrical engineering. Okay, these are important concepts. Going to be, oh yeah, I should mention, not going to have class Monday or Tuesday. My grandson, who's an electrical engineer, is coming in Eastern Virginia. And then we're going to drive to Indianapolis. Hopefully not get stuck in gridlock for too long. And hopefully get to Sandy Cliffs. At least get to see it get dark. Likely to be cloudy, but a chance. Haven't checked the weather forecast for the last couple of days, but we're getting within a few days of it. Should be pretty active. Okay. Now, the whole point is, I want to run this by you. See a couple of things. You know, see his education. Better to think about this hypothetical case. Without putting them on the spot, you know, just have throw out a problem and see what he thinks. You see what his perspective on it, to see how he thinks through it. Okay, then ask them. Board members have things like this. To be a power systems engineer. You know, you might not do power systems, but other forms of electrical engineering, but other things, even kind of electrical engineering, this could be relevant. So you might have an interesting discussion. All right. Okay, in situation I described with superconductors and so forth, if you can actually set it up and use this regular old capacitor, it doesn't carry all that much energy when it's fully charged. You could supply a lot of power and charge that thing really, really fast. Okay, probably in femtoseconds. And you could work out what's your superconductor, how many charges are available. Okay, so if electrons can migrate at 1/10 the speed of light, how fast would that charge a given capacitor? Okay. And how much power would it take? And there's some feedback stuff in there. You'd end up with a system differential equations. Be interesting problem, but whether it's of any practical use. As far as understanding capacitors, I think it's worth thinking about. So same situation, except now we've got a resistor here, got a capacitor here, and we've got a source voltage here. We throw the switch. How quickly does a capacitor charge in that case? Okay, well, let's say similar situation here, you throw a resistor in. Now, throwing a resistor into a superconducting circuit is tricky, so let's just pretend we can do it. Okay. You know, maybe everything's superconducting in there and we somehow have a superconducting terminal up to some terminal there, and then there's resistance external to the stuff. Or we'll just put a regular old resistor in there that is not made of material that becomes superconducting. Okay. So when you throw the switch, there's no question there's a voltage across the stuff. Okay. So there's no question there has to be some current. On the other hand, you have a parallel combination of a resistance with zero resistance, which is basically a short circuit, and nothing is supposed to go through. You have an infinite ratio of resistance from this resistance. The ratio of this resistance to this is infinite, so all the current should go through this. Now there are all kinds of contradictions in that and all kinds of second order effects that you probably have to think about. Okay. So that's just kind of an interesting conundrum. But we're not going to pursue it. Still, just by thinking about this, you have to think through a lot of stuff. You have to think through some limits and you have to apply some situation that you develop in calculus. I think you develop significant amount of stuff. Reasons about thinking about this. Now we've got a source resistance. I think we got that. There it is. There's a source resistance. Okay. Now what's going to happen? Well, first of all, the voltage out here is going to be a little less than the voltage of the source, or the voltage of the cells. They just And it's going to be variable because as the current changes, the voltage drop across this source resistance is going to change, right? Because the more current you got flowing through this thing, the more resistance, the more voltage drop. Okay, so more current, more voltage drop, less voltage through the source. And we'll be measuring some of that. Attempting to measure lab. So conceptually, now what's going to happen to capacitor? What's going to happen to this resistance? We're still going to assume zero or negligible resistance in this part of the circuit. Okay. So basically, you're not going to get an infinite current because of this. You know, your current can't exceed what it would take to make the voltage drop here equal opposite to voltage here. Okay. So if your current's too big, you get more voltage drop across here than you have from your cells, your source. Okay. So your voltage can't, your current can't ever well, what is the expression? It's the maximum current you could possibly have. Okay, well, you know, it's fairly easy to figure what the limit of I is. If the voltage across this resistor is equal to the voltage of your cells, okay, then you're not going to get any current. You're not going to have any voltage coming out of it. You're going to have a net voltage from here to here of zero. And for what current would that be? Well, I want to write out a statement on what no current if the voltage drop across RS is equal to DS. Actually, I have to write it out. Still, you got cells. Okay. So R times RS has to be less than DS. And it's certainly possible. Well, I mean, that makes when you close the circuit, you're not going to get anything near an infinite current through here. You're going to get this much current. Okay. Well, then it gets pretty complicated, and we're not requiring differential equations as a prerequisite or co-requisite or any kind of requisite for this course. But since you've had differential equations, you can at least understand that now you're going to have a varying current that depends on how much charge you have on the capacitor, right? But the voltage here also depends on how much charge you have on the capacitor, not the net voltage around the circuit, but the voltage between here and here, Because as your current, if you're charging the capacitor, your current's going to decrease. You've experienced that whenever you crank the capacitor and it gets easier to crank. Because current times voltage decreases since your current decreases. Okay. Well, anyhow. So it's more complicated than just a simple RC circuit when you have a source resistance. Okay. That includes when you charge a real capacitor. Includes when we charge capacitors here. You get more and more voltage across your source, across your battery, let's say, as your capacitor charges. Because you have less and less current through the internal resistors. That's modeling that. As I said, goes beyond the scope of the course, but it's another important thing to think about when you think about circuits. Let's just consider this circuit. Let's assume valuable internal resistance, because as that last example shows, if you understand what I was going to tell you, and I think you do, that really complicates things. Okay, internal resistance really complicates things when you have a variable or a varying current, as you would if you're charging fast. Okay. Fortunately, your internal resistance is usually a lot lower than the other resistances in the circuit. So we're just going to assume that. So what can you tell me about this situation? Well, first of all, you know, you're going to have a current I1 and a current I2. Makes sense. And you know, I'm drawing loop diagrams. And you're going to have a current here. You're going to have a current here. And you're going to have a current here. There are three currents. Current here has to be the same all the way from here to here because there's no branching point. Current here is going to be presumably depending on your right, pretty different than the current here. Okay. So you got I1, I2, I3. Now I3 is good from here to here because again there's no branch. Okay. And whatever's being deposited here is being pulled off of this one. So the current both sides answer has to be same. That's a subtle difference, maybe. Suddenly think about in the middle of a test when it freaks me out. So, okay. So what are you going to do with that information? Well, this is more complicated than simple parallel and series resistances and series of parallel capacitances, because you got resistance with this capacitance. Don't have any resistance with this capacitance, but resistance here, give us source here. It's getting out of control. So again, there's a limit to what we can do with this in this course. We just want to be thinking about, think about what goes on. So it's going to lead to differential equations because your capacitors keep changing their charge, their voltage, and so forth. But my recommendation is to write out what you can with Kirchhoff's laws. See if you can write at least a system of equations that maybe we could then make some sense of. Okay, so if we use Kirchhoff's laws here, first of all, it's pretty clear that I1 minus I2 minus I3 equals 0. Usually I write these in an equals 0 format, but if you write I1 equals I2 plus I3, it's obvious. That's okay. But often we're going to solve these equations by elimination, and you kind of want to get your curves lined up and get all these things done. Okay. And you also point out source points. Okay. Now, if we go around this board, I'll just call this. So around the loop that I sketched, purple, our voltage drops are what? Well, I1 R1 maybe like this. Okay. And then we'll worry about what the voltage across the capacitor happens. Okay, so now for this one, yeah, we have I3R3 plus supporting cross capacitor 2 equals 0. Well, then you have VC1 equals Q1 over C2, VC2 equals Q2 over C2. For Q1 and Q2 would be functions of time. Then dQ1 dt the DQ2, DQ, what are they? Well, what's DQ1, DT? Q1's a charge and C1, I2 is the current through C1. That's I2. I2 is basically how much the rate at which you pull a charge off of this and depositing it on this. And DQ1 DT is I3. Now there are things about signs that I don't want to get into. This and probably taking somebody defines it on board occasions and so forth. This is going to lead to an interesting system of differential equations when you rewrite the system. Got I1 minus I2 minus I3. Got I1 R1 plus DC1. What's DC1? Well, it's Q1 over C1. And you got your I3R3. Plus DC2. I've got this messed up. Okay. So far, it doesn't seem particularly informative, but I3, which is over here, can be replaced by DQ1 DT. My I3R3, which is going to be R3 DQ1 DT. And I2 is R2 DQ2 DT. Okay. Then, and that should be minus. Then I1 is just going to be R2 DQ2 DT dot. Okay. So that we can replace I1, which is equal to the sum of these, and we get R1 times R2 DQ2 DT plus R3 DQ1 plus V1 over C1 minus DS equals 0. And then we have our second equation, R3 dQ1 dt plus Q2 over C2. So this is a linear system of differential equations in Q1 and Q2. Now we're not going to solve it. Because as you recall, that's a little bit involved. Okay. It's something that if and when, and this sort of thing will occur in your future. Okay. If you're in electrical engineering, and if you're in mechanical engineering, you get mechanical analogs of this. And that's what pretty much everybody that applies in one or the other, or aiming at one or the other. Okay. So there's just a little connection. Benefit thinking about all this is it just deepens your thinking about circuits. So the stuff you got to do for homework starts to seem pretty easy. Okay. This is not that hard. I mean, you got to turn the crank method for solving systems of differential equations. It's just that, you know, you knew it a few months ago, probably for your final. You haven't used it since then, so it's faded a little bit, but it'll come right back. It's not difficult. Okay, moderately difficult.